Dear students, in this module, you shall be able to know about carboranes, know about types of carboranes, and learn about various methods of preparation of carboranes. Let us first know what are carboranes. Carboranes have been known for more than half century, but attracted mainly the theoreticians who wanted to know their structure and bonding, and also small group of industrial researchers who recognized their potential for creating extremely heat stable polymers. Carboranes are polyhedral boron carbon molecules or clusters stabilized by electron delocalized covalent bonding in skeletal framework. The characteristic feature of carboranes is the presence of one or more carbon atoms in electron delocalized boron cluster framework. As the skeletal carbon and boron atoms are involved in delocalized bonding, each typically having 5 or 6 neighbors including hydrogen or other attached substituents, these molecules are non-classical and their structure cannot be described in terms of usual organic bond diagrams in which a connecting line between two atoms explicitly indicates an electron pair. In structures which are described connecting lines show the polyhedral geometry only and do not in general represent electron pairs. The range of composition in carborane cages extends from boron rich clusters such as C2B10H12 and CB11H12- having as many as 6 skeletal carbon atoms, but those with high boron content are dominant. Consequently, in most theoretical treatments of structure and bonding, carboranes are treated as polyhedral boranes in which one or more skeletal boron atoms are replaced by carbon. The basic principles of bonding in boron clusters are well understood after decades of study, and in recent years the advent of density functional theory, that is DFT, and other powerful computational tools has led to major advances in correlation of electronic structures with their geometry, their reactivity, bond strength, NMR shifts, coupling constants, vibrational frequencies, and other properties. Now let us look at the structure of carboranes. A carborane is a cluster composed of boron, carbon, and hydrogen atoms. Like many of the related boranes, these clusters are polyhedra and are similarly classified as closo, nido, arachno, hypo, etc. based on whether they represent a complete polyhedron or a polyhedron that is missing one or two or more vertices. The number of valence electrons in carbon atom is equal to those of boron atom plus a hydrogen atom. Hence, BH unit can be substituted by carbon in carboranes. Now, depending on their geometry, the carboranes are classified as closo, nido, arachno, hypo, and conjuncto. Let us see one by one what these geometries are. The closo structures, which represents a close polyhedra, these structures are adopted by borane anions having a general formula BnHn2-, where N can range from 6 to 12 atoms. These structures are also adopted by carboranes having a general formula C2Bn-2Hn, where N can range from 5 to 12, and related isoelectronic species. Their N skeletal boron or carbon atoms define the vertices of a triangular faced polyhedra as shown in the following figure. In these figures, you may note that all the polyhedras have the triangular faces and they are closed figures. Depending on the closed structures of polyhedron, they may be classified as carboranes. The same polyhedral serve as the basis of the structures of nido and arachno compounds too, although for these boranes and carboranes the polyhedras are incomplete. That is, they are either missing one or more vertices. If they are missing one vertices, they will be characterized as nidocarboranes. If they are missing two vertices, they will be characterized as arachno compounds. Now let us look at the nido structures. Nido structures are adopted by neutral boranes having a general formula BnHn+4, and also the carboranes with general formula CBn-1HN+3 and C2Bn-2HN+2, C3N-3N+1 and C4Bn-4HN and related ionic species, whose n-skeletal boron or carbon atoms occupy all but one of the vertices of the appropriate n+1 vertex polyhedron. Similarly, in arachno structures, there are two missing vertices. These structures are adopted by boranes having a general formula BnHn+6 and isoelectronic carboranes such as C2Bn-2HN+4, etc. Their n-skeletal atoms define all but two of the vertices of the appropriate n+2 vertex polyhedron. The formulas of typical closo, nido and arachnoboranes and carboranes are listed in the following table. As you can see, the examples of typical closo, nido and arachnoboranes and carboranes are given here. Just look at the number of skeletal bond pairs. When the number of skeletal bond pairs is 6 and the number of polyhedron vertices is 5, the fundamental geometry is trigonal bipyramidal. For example, in case of closocarboranes, this trigonal bipyramidal geometry is represented by C2B3H5, and in arachno species it is represented as B3H6-. When the number of skeletal bond pairs is equal to 7 and the number of polyhedron vertices is 6, the geometry is octahedron. The examples in case of closo species is B6H6-. In case of carboranes of closo type, this is represented by CB5H7 and also C2B4H6. In case of nido, this geometry is shown by B5H9, and in carboranes nido type it is shown by C2B8H7. For arachno species, this geometry is represented by B4H10. Similarly, with skeletal bonded pairs 8 and the number of polyhedron vertices 7, the geometry is pentagonal bipyramidal. The examples in case of closo is B7H7 2- and carboranes such as C3B5H7. The nidoboranes under this geometry is B4H10 and B6H11, and the carboranes CXB5-X, H10-X, where X can range from 1 to 4. In case of arachno species, this is represented by B5H11. When the number of skeletal bonded pairs are 9 and number of polyhedron vertices are 8, the geometry is dodecahedral, that is D2D. The examples under closo species are B8H8 2-, and in case of carboranes closo type, the examples are B6H8 and C3B5H7. Under the category of arachnospecies, this is represented by B6H11. Now, when the skeletal bonded pairs are 10 and the number of polyhedron vortices are 9, the geometry is tri-capped trigonal prism, also known as D3H. Under the category of closospecies, the examples are B9, H9, 2- and C2, B7, H9. Under the category of nidospecies, B8, H12 and C2, B2, H10. When the number of skeletal bonded pairs are 11 and the number of polyhedron vortices are 10, the geometry is bicapped. The geometry is archinidum antiprism or D4D. Examples under the closospecies are CB3, H10, 2- and C2, B5, H10. Under the nidospecies, B8, H12- and C2, B7, H11. Under the arachnospecies, the example is B8, H14. Moving on further, when the number of skeletal bonded pairs are 12 and the number of polyhedron vortices are 11, the geometry is octadecahedron, also called C2D. Examples under closospecies are B11, H11, 2-. Another one is C, B10, H11. Yet another one is C2, B2, H11. Under nidospecies, the examples of octahedron species, octadecahedron species is B10, H14 and C, B9, H13. Also C2, B8, H12. Under the category of arachnospecies, the examples are B9, H15 and C2, B7, H13. Now, when the number of skeletal bonded pairs are 13 and the number of polyhedron vortices are 12, the geometry is icosahedron, also represented as IH. The examples under closospecies are B12, H12, 2- and B11, H12- and C2, B10, H12. Under the nidospecies, the examples are C, B10, H13 and C2, B9, H11, 2-. Also C4, B7, H11. Under the category of arachnospecies, the examples for icosahedron are it is B10, H15- and B10, H14-. Now, apart from these, the hypocarboranes, herein, as I said, there are two missing vertices in a closed polyhedron. These structures are adopted by those carboranes having a general formula C2, Bn-2, Hn+6, wherein three vertices are missing from the parent closocarborane. I am repeating this. In case of hypo, as I said earlier, the hypostructures are adopted by carboranes wherein three vertices are missing from parent closocarborane. The general formula for compounds which adopt hypostructures are C2, Bn-2, Hn+6. The next category of carboranes are conjunctocarboranes. These carboranes are formed by joining two or more preceding type of geometries, that is either a combination of arachno or nido or a combination of closo or hypo or any other combination. This will come under the category of conjunctocarboranes. The position of hydrogen atoms in boranes and carboranes are worth noting. In closoborane anions, that is in BnHn2-, the NBH units are aligned so that the BH bonds point radially outward away from the centers of the Bn polyhedral and are referred to as exo-BH bonds. The CH units of isoelectronic closocarboranes having general formula C Bn-1 Hn- or C2 Bn-2 Hn are similarly oriented. When anions like Bn Hn2- and C Bn-1 Hn- are protonated to form Bn Hn+1- and C Bn-1 H+1, the extra hydrogen atom apparently occupies a bridging position either between the two boron atoms, which are lying over an edge of the n-cornered polyhedron, or for three atoms over a polyhedron face. This has been supported by microwave spectroscopic study. Let us see the structures of closocarboranes now. For example, we start with 1,6-dicarba-closohexaborane having the formula C2B4H6. Here the two carbon atoms are named as dicarba, and because in all we have 6 atoms including 4 borons and 2 carbons, we call it hexaborane. So the name 1,6-dicarba-closohexaborane. It has a regular octahedron structure as shown in the figure, where 4 boron atoms are present in one plane and the 2 carbon atoms are present above and below the plane containing the boron atoms. It has a closed symmetrical structure and hence a closocarborane. You can easily see in the figure that all the vertices of this polyhedron are occupied either by carbon or by boron atoms. Another example of closocarborane is 2,4-dicarba-closoheptaborane having the formula C2B5H7. In this figure, you can see that the white balls are representing boron atoms and the black balls represent carbon atoms. In all, there are 7 vertices and hence the name heptaborane. Since there are 2 carbon atoms, we call it dicarba-heptaborane. Since all the vertices of this polyhedra have been occupied either by boron atoms or by carbon atoms, this forms an example of closocarboranes. Look at another example, 1,7-dicarba-closooctaborane having the formula C2B6H8. Here also we have 8 vertices occupied either by boron atoms or by carbon atoms, giving a closed polyhedra and hence the name closocarborane. Few more examples of closocarborane includes 1,6-dicarba-closononaborane and 1,10-dicarba-closodecaborane having the formula C2B8H10. Each of the polyhedron vertices have been occupied either by carbon or by boron atoms. Another example of closocarborane is 2,3-dicarba-closoundecaborane having the formula C2B9H11. Now moving on to the nidocarboranes. As we have already mentioned that in nidocarboranes, one of the vertices is missing as compared to a regular polyhedra. For example, the nidocarboranes are having a general formula C2BN-2 HN+2. Let us take the example C2B4H8. In this compound, only 4 vertices N-2 are occupied by boron atoms of the regular 6-cornered octahedron with N vertices, and 2 of the vertices are occupied by carbon atoms. Note in this structure that one vertex is missing. Now let us see the structure of arachnocarboranes. The general formula for arachnocarboranes is C2BN-2 HN+4. Let us see this example where we have the structure of C2B8 H10 4-. Note in this structure that 2 vertices are missing as per the regular polyhedron structure. Now let us discuss the bonding in carboranes. Bonding in carboranes is governed by certain rules called Wade-Mingo rules. These rules are named after the scientist who formulated them. The names of these scientists are Kenneth Wade and David Michael Patrick Mingos, collectively known as Wade-Mingo rules for the bonding in carboranes. In order to rationalize the structure of carboranes, a scheme of skeletal electron counting was developed, to which the following rules are applicable. Let us see what are these rules. Step 1. First, the number of skeletal electrons are calculated as the sum of the following contributions. Each BH bond contributes 2 electrons. Each CH bond contributes 3 electrons. Each additional hydrogen contributes 1 electron. Finally, the anionic charge on the cluster is to be added to above contributions. That is, the skeletal electron count should be equal to twice of BH bonds plus thrice of CH bonds plus 1 for each additional hydrogen and plus the total anionic charge on the cluster. Now step 2. We then calculate the number of pairs of electrons, which is equal to the skeletal electron count divided by 2. Now step 3. Let the number of vertices, that is the number of boron and carbon atoms, is given by n. Then by comparing the number of electron pairs with the number of vertices, the cluster structure can be identified. As given in the following table, if the number of electron pairs comes out as n+1, the type of borane structure is closo. When the number of electron pairs is n+2, the type of borane is nido. When the number of electron pairs is n+3, the type of borane is arachno. When the number of electron pairs is n+4, the type of borane is hypo. Now let us first discuss about the closocarboranes. These have a completely closed triangular polyhedral structure in which all the vertices of the triangular polyhedral structure are occupied by either boron or carbon atoms. There are n+1 electron pairs present in multi-center bonding orbitals of the skeletal structure of closocarborane, where n is the total number of boron and carbon atoms. For example, C2B10H12. In this compound, n is equal to 12, that is the total number of carbon and boron atoms. According to Wade's rule, the 2 CH units contribute 2 multiplied by 3 6 electrons, and 10 BH units contribute 10 multiplied by 2, that is 20 electrons, to the bonding molecular orbitals or the structural skeleton. Thus, there are 13 electron pairs present in the multi-center bonding orbitals of C2B10H12, and hence it is a closocarborane. Nidocarboranes. These carboranes may be assumed to be derived from the closo-triangular polyhedral structure of a closocarborane by removal of one of the vertices of the polyhedron. The resulting nido, that is a nest-like structure, has n+2 electron pairs in its multicenter bonding orbitals. In nido C2B4H8, n is equals to 2 plus 4, that is 6. So, to calculate the skeletal electrons, we say the 2 CH units contributes 2 multiplied by 3, 6 electrons, and the 4 BH units contribute 4 multiplied by 2, that is 8 electrons, and the 2 extra hydrogens contribute 2 electrons to the bonding orbitals of the skeletal structure of nido 2,3 C2B4H8. Thus, there are 8 electron pairs in the multicenter bonding orbitals of the skeletal structure of the carborane, hence the nido structure. In arachnocarboranes, the structure of this type of carboranes may be assumed to have been derived from nido structures by removal of the vertices of these structures. There are n+3 electron pairs in the multicenter orbitals of carboranes. For example, C2B7H13, which fits into the formula of n+3 formula. Now, let us see the important features of bonding in carboranes. The triangular faced polyhedra shown in the figure form the basis for the structures of boranes and carboranes. The skeletal boron or carbon atoms occupy all but one or all but two of the vertices of the appropriate polyhedron in closo, nido or arachno compounds respectively. Each skeletal boron or carbon atom has a hydrogen atom or some other singly bonded ligand terminally attached to it by a bond radiating outward, that is exobond, which is away from the center of the polyhedron to which a pair of electrons is allocated. The remaining valence chain electrons that are known as bonded pairs are regarded as skeletal bonding electrons, represented as B pairs. Each skeletal boron or carbon is considered to provide 3 atomic orbitals for skeletal bonding. The symmetries of the polyhedra are such as to generate n+1 skeletal bonding molecular orbitals from these atomic orbitals, where n stands for number of polyhedron vertices and n is equals to b minus 1. Compounds with skeletal atoms and B skeletal bonded pairs adopt closo structures if B is equals to A plus 1, nido structures if B is equals to A plus 2, and arachno structures if B is equals to A plus 3. Now let us summarize what we have learned. We have learned that the carboranes are compounds with the basic structural unit containing a number of carbon and boron atoms arranged on the vertices of a triangular polyhedron. We have also learned that the structures of carboranes are closely related to those of isoelectronic boranes, wherein BH is same as B minus, which is same as 1 carbon, and BH2 is same as BH minus or BL or CH. We have also learned that the structure of carboranes can be predicted with the help of Wade-Mingo rules. We have also understood that the carbon and boron atoms in closo structures are numbered in such a manner that the top vertex is given number 1 and the remaining vertices are numbered in the clockwise direction.